Now we're going to look at stationary points. So far we've been looking at functions y equals f of x. We're going to do something a little bit different now, and we'll say that s is equal to f of t. So this is exactly the same thing. Nothing is different mathematically, but I'm using different names for the variables. The reason is I want s here to be a displacement, or the distance travelled by some object, and t to be the time. So we're looking at distance travelled as a function of time. And let's say it looks like that. So an object that goes out and then back and then out and then back again. So s here is the displacement and t is the time. The derivative here, ds dt, is the rate of change of displacement with respect to time, which is velocity. So that the rate of change of distance with respect to time is speed or velocity. If s was in meters and t was in seconds, velocity would be in meters per second, because you would calculate it by dividing distance in meters by time in seconds. There's a few points on this curve where the tangent to the curve would be flat. So right here, and right here. Remember that ds dt, the derivative of s with respect to t, is the rate of change of displacement with respect to time. In this graph of displacement against time, it is the slope of the tangent to the curve at a given point. So at each of those points, the curve is flat, or the tangent is horizontal. So the velocity is 0. If the velocity is 0, then the object, in this case, is stationary, not moving. So these are the stationary points. In this case, the stationary points are points where an object is literally not moving or stationary. But in general, for a function y equals f of x, a point x1, y1 is called a stationary point if the derivative at that point is equal to 0. There are three kinds of stationary points that we're interested in. The first is a stationary point like this. At this point on the curve, the tangent is flat or horizontal. The rate of change of y with respect to x at that point is 0. It's a stationary point. In particular, that is what we would call a local maximum. If that point is at position x1 and y1, then it's a local maximum if y1 is greater than all the other points in the immediate neighbourhood of the point x1, y1. We say it's a local maximum because this curve could reach higher y values somewhere else, but just not in the immediate neighbourhood of that stationary point. So that's the local maximum. The next possibility is a local minimum. For example, if a function looks like this, we have a stationary point here where that y value is the smallest y value out of all the y values in that immediate neighbourhood. So if that's my point x1 and there's y1, my value at that point, that point x1, y1 is a local minimum if y1 is less than all the other y values in the immediate neighbourhood of that point. There's one more possibility for a smooth function to have a stationary point and for it not to be a local maximum or a local minimum. It looks like this. So this point right here, the tangent is flat, or a slope of 0. dy dx is 0 at that point, but it doesn't turn around. So it goes flat and then it carries on upwards. That's what you would call a stationary point of inflection. We'll talk about points of inflection later on. So let's look at one way we can tell if we're looking at a local maximum or a local minimum, if we don't have the thing plotted out in front of us where it's obvious. Well, if we look at the slope at some various points, say before and after the stationary point, Here before the stationary point, the tangent is like this, and after the tangent is like this. So if you look here on the left, that's a positive slope, and on the right, that's a negative slope. So if we have a local maximum at some point x1, y1, we must have dy dx equal to 0 at the point. We must have dy dx positive or greater than 0 on the left. So immediately to the left of my stationary point, I should have positive slope for a maximum like this. And dy dx should be negative or less than 0 on the right. So you can see that for a local maximum, the tangent to that curve has a positive slope to the left. As you come around the top, it goes flat, that's your stationary point. And as you come over the top, that tangent becomes negative again on the right. So you go positive, 0, and then negative. For a local min, we have dy dx equal to 0 again at the point. Before the point, for a minimum, we have a negative slope like this, and after the point, we have a positive slope. So here, the derivative dy dx is going to be negative or less than 0 on the left. And dy dx is going to be greater than 0 on the right. For the stationary point of inflection, here the rate of change is positive here. It goes to 0 at this point of inflection, or at the stationary point, and then it goes back to being positive. So there's no change in the sign. So that is the three kinds of stationary points that we look at, and the first derivative test that would tell you whether you have a local maximum, a local minimum, or a stationary point of inflection by looking at how the derivative, or the rate of change of y with respect to x, is different on the left side and on the right side of your stationary point where it's equal to 0. So you'd use this test if you don't have the thing plotted out in front of you already. So there it is, stationary points and the first derivative test.